Hey, team! Oh my goodness. Oh, hi. We got Benthoven, no relation, and Creationist in the side chat. I think there's about 9 or 10 people watching. Thank you so much for joining us tonight. Dapper was kind enough to come hang out. And
an opportunity to rag on Matt Powell, how could I pass that up?
This is true. Yeah. Yeah, team, I thought we would take a break from doing climate science. Just, you got to mix things up a little bit. And I found some Matt Powell videos.
Painful.
And they're not great.
Yeah.
Well, I guess I haven't actually watched these yet, so I don't know that for sure. But
okay, I've never had my toenails ripped out by hot pokers, but I'm still pretty sure it's not going to be great.
Yeah. Should we just jump into it? Because I'm super excited.
Yeah, let's go for it. Let's see what horrifying videos you have found for us to watch.
Yeah. Okay. So this is just Matt Powell's homepage. I was looking for science videos of his that address my neck of the woods science-wise. Let's start off with something nice and light, just kind of a softball. Let's look at some zircon crystals.
You gotta love zircons.
Yeah, gotta love zircon. Zircons are like my favorite mineral. They're very cool.
Hey guys, this is Matt Powell.
Hey Matt.
Hey Matt. Is it bad that I'm immediately like, oh, huzzah, he's not wearing his Russian mob tracksuit?
No, though, I appreciate that he's instead wearing a somewhat too tight flannel shirt.
Yeah, you gotta appreciate the button down. It's good. You know what? Like, I wasn't gonna comment on the too tight, right? I bet none of our clothes fit great these days.
That's fair.
Yeah.
At least he doesn't have the top button buttoned, because I see that with a lot of sort of not quite professional tier creationists. You get that top button for no reason. Like, you don't have a tie on, so why are you buttoning that? Because this is like a fashion tips with Dapper. If you have a button-down shirt, the only real reason to button that top button is if you have a tie on.
Mm-hmm. But what about when you're wearing a tie with no shirt, Dapper?
Well, then you don't have to button the button.
Yeah. Also, hi, Rebecca. Oh my goodness, there's so many people in chat. Thank you guys for joining. And maybe we will get to see Dr. Peel.
Yeah, well, let's hope so.
Fingers crossed, really. Okay. All right, well, I'll actually let him talk.
Young Earth is the fact that we actually find helium inside of rock crystals. Now, helium actually slips out of the rocks over time. And so
all right, let's calm down on that for a second. Helium also, so these are, what he's talking about are alpha particles that are emitted from the alpha decay of, specifically, if he's talking about zircons, and he's talking about the uranium to lead decay chain, which is mostly a series of alpha decays. There's some beta minus slip in there eventually. An alpha particle is just the nucleus of a helium atom.
For those of you not in the know, beta minus decay is shooting out electrons.
Yeah.
Because I always found it a little bit odd that you don't just call it electron radiation. You're like, no, it's beta minus.
It's a beta minus particle.
But those are just electrons, right? It's like, yep. But
yeah, no, it's a science history thing, right? Because when beta radiation was first discovered, they did not know that these were electrons, so they didn't know what they were. They knew they were different from alpha particles. And sorry, Dapper, I know you know this, but anyway.
Well, hey, it's for the audience, right?
Yeah, for the audience.
Not everyone went to school and learned about nuclear decay processes.
We
did.
Was that just you and me? Yeah.
Yeah, basically. So the fact that I might know something doesn't mean that you shouldn't explain it. Mm-hmm.
So when this alpha particle is made out of this decay chain, right, when you get this helium atom, and it is just the nucleus, right, it is a gas, right? So it's one atom, it's in its gaseous state, and it's pretty diffuse, right? So that helium atom is going to be able to move around and eventually escape from the rock. That's definitely a function of temperature. Yeah, the warmer it is.
I'm sorry, Don Giovanni asked an interesting question, which is there positron decay? And beta plus decay is a thing, and that releases positrons, yeah.
Yeah. So yes, you can. So what happens in beta minus decay, beta minus decay and beta plus. So in beta minus decay, what happens is you have a so you have a neutron, and you destroy that neutron. That neutron is going to turn into a proton. But if it turns into a proton, we have to balance charge. You have to balance charge and spin. So if you destroy a neutron, you're going to make a proton and electron to balance charge, and you're going to make an antineutrino to balance spin. If you're going to do beta plus decay, then you're going to turn a proton into a neutron. So we destroy that positive charge. So you've got to replace the positive charge so that the whole reaction is charge neutral. So the proton turns into a neutron, a positron, and a neutrino. Anyhow, that's stuff I carry around in my head still.
Yay for antimatter.
Yay for antimatter. Yeah. So, cool. David Oliver, I have heard this rumor that Matt Powell has a giant inflatable banana in his backyard called Dr. Peel.
I don't think it's just a rumor. I'm pretty sure it's completely accurate.
Yeah.
At least by Matt Powell's evidentiary standards.
Mm-hmm. Okay, so he talks about that these like gas can like slip out, or I think he says helium. Anyway, I just wanted to explain what we were actually talking about. Goodness. Okay.
I suppose you've probably seen, rock crystals that actually have air bubbles inside of them. And those
You're not seeing these bubbles,
are
Matt.
actually helium.
No, those air bubbles are not
goodness.
helium, good sir.
Oh, that's dumb.
Oh no, because these are emitted one atom at a time, team.
Right.
Like this is not an air bubble. This isn't an air pocket. It's just single helium atoms. So, okay, sorry, brain collapsed there for a second. I was trying to think of if I've ever seen an air bubble caught in a rock. I've seen in basalts, right, where you see where it outgases really fast because it forms so quickly.
Generally, though, you're not going to see a visible air pocket in a zircon crystal.
No, certainly not in a zircon crystal.
It's not going to happen.
Yeah.
The thing about zircon is that it's a relatively slow-forming crystal, and it's relatively dense and hard. And so, basically, it tends to exclude gases when it forms, which is one of the reasons that you can, like many crystals, that you can reasonably assume that it has a fairly closed system in terms of radiometric dating, right? It's because this is a crystal which you would not typically associate with entrapped gases, because the crystal matrix doesn't really have a spot for them. And so as the crystal initially forms, it's not going to have many of these things. And it's certainly not going to have an air bubble, because that would just float up and out, because, spoiler alert, air is less dense than rock. And so if you have a bubble of air in molten rock, it's going to go up.
Yeah, absolutely. Also, zircons don't form in, like I mentioned, basalts is where I was thinking of. You would see like rapid outgassing, where you can see that in the rock. That's not the type of rock that a zircon's going to form in. And we got a great question. Protons were so stable, we can't sure they'll literally ever decay. So what happens when you get beta plus decay? What's going on there is it's in the nucleus of an atom. If you have way more protons than neutrons, that's an unstable energy state, and it would be more stable if this proton became a neutron. So what you're thinking about there are like protons in the wild.
Yeah.
Not trapped in a nucleus.
Yeah, like an He4 or helium-4, which is what you're getting with the alpha particles. Those protons may not ever decay.
Yeah.
But if you have some gigantic, like one of those crazy synthetic elements or something that has just a stupid high number of protons,
right?
Well, that probably won't stick around.
Right. By the way, this was, if anybody knows what an electron well diagram is, that's what I was drawing with my hands in imaginary. That was.
Oh, that reminds me. Speaking of electrons and energy levels and whatnot, I encountered someone who's had an argument for God that kind of went like, if there were no God, then we would expect electrons to spiral in and collide with the nucleus. And it's like, oh, you don't know about quantized energy.
Force?
Yeah, apparently. And it's just like, not only is God the nuclear weak force, but apparently God also is the one who enforces the quantized energy states of electrons.
Right. I mean,
and it's just like, no, none of that.
That's why, Dapper, didn't you know? That's why he's so busy.
Oh, I mean, there are a lot of electrons that he's trying to police right now.
There's a lot of electrons to keep track of. And
like,
so,
no, you can't have fractions of a quantum of energy. Stop it.
Yeah. Yeah. So yeah, that's a very cool point. I hope my explanation made sense, because that's thinking about, again, protons in the wild by themselves, not in the nucleus of an atom. Okay, wow. So before we started streaming, I told Dapper I'd picked out like 3 or 4 different videos, and your response was, "Whoa, Maddie, that's a lot." And I said, "Well, they're only a few minutes each. We're 23 seconds into this video and 11 minutes into the stream. So you were right. I was wrong."
Yeah, Matt Powell videos are dense and dumb.
At least they're short. Like,
they would have to be. I can't imagine how we can keep up that much conscious thought for much more than a few minutes.
Yeah. Okay.
And over time, that helium will slip out. And so this actually proves that the Earth cannot be billions of years old.
How
just
so?
due to the fact that the helium would...
That's not a zircon, is it? I think that's just quartz.
I mean, it's hard for me to see, but it looks very, very big, and most zircon crystals are very, very small.
Itty bitty. Yeah.
Yeah.
Okay.
Because the thing is, most of the places that you find zircon are actually worked into other igneous rocks, and often they're much younger than the igneous rocks. Much older than the younger igneous rocks that they're worked into.
Right.
So,
like the oldest zircon we've ever measured is on Earth is 4.5 billion, but the oldest rock is like 4.1 billion.
Right. And one of the things about zircons is that they're basically immortal. Once they form, they're not going away. They can fracture and splinter, which is why many of them are so small. But they're never going to melt again, most likely.
Exactly. I'm sure he's referencing rate, and I've talked about that on a previous live stream.
Oh yeah.
Yeah. So
my favorite fact about rate is that rate concluded that all of the science worked for an old Earth, and they didn't have a non-magical solution to the heat problems. Rate was a complete failure by its own admission.
That's amazing.
That's all you need to know about rate, is that when a bunch of creationists, professional creationists, tried as hard as they could for like a decade to come up with a single shred of evidence, they basically came up to the conclusion that no, you have to just invent miracles in order to make the Earth young.
Yeah.
Which, I mean, okay, sure. Miracles all the way down.
Miracles all the way down. Are you being sarcastic, or did you find a real example of accelerated decay?
I mean, unless we're talking about like induced fission in a reactor, I doubt it.
Oh, okay. Yeah.
Yeah, as Creationist points out, quote unquote exotic solutions was the phrase they use, because they don't want to just say miracle.
Okay, so David, nuclear radiation doesn't hasten decay. It can hasten induced nuclear reactions, not spontaneous nuclear reactions. Those are very different things. And it's spontaneous nuclear reactions that you can't change the decay rate. So this is Rebecca's example. We have something that undergoes beta decay if there are no electrons in the way. I will have to look into that. I'm going to take a note, and I'm going to look that up after stream, because I would like to read about that. So 163. Thank you for doing that legwork.
Yeah, that would be pretty cool to look at. I would also wonder how applicable it is to any of the radiometrically significant isotopes, because I'm going to go ahead and guess probably not very significant to those, but it's still very cool.
It's still very cool. So yeah, I want to read into that and look at it later. Okay, so he was talking about zircons, and he was going to say how the presence. So what he's going to say is that because you can still find helium in, there's still helium in some rocks, right? Therefore, but all that helium should have diffused by now. So therefore, God. I think that's what we're going to go.
Well,
with.
Therefore, the Earth is young. Therefore, God. He's going to. He's probably going to have that extra step in there.
Fair. Okay, so let's see him make that argument.
Slipped out of those rocks by now. But if you Google how old are crystals, the first thing that pops up is that they're the oldest crust of the Earth. Now, according to evolution,
what a weird thing
is
to Google.
4.5 billion years old. And so to say that helium has been sitting inside of rock crystals and has not slipped out by now.
It's also driving me nuts that he keeps saying slipped out when like diffused is the right term.
Right.
Like that's such a nitpicky thing. And normally like with non-specialists, I'm not going to bother them about like language as long as they're communicating clearly. But like he keeps using slipped out over and over and over and over. Like he thinks that's the right word, and it's really bothering me. So diffused or outgassed, those would be the right words.
Now, one thing is, I don't know of anyone who's saying that all helium currently in zircons is primordial to the zircons.
Right.
Because zircons don't form with helium in them. That would, in fact, outgas before the zircon formed. The zircons that are in there are, like you said, the products of nuclear decay within the zircon. You have a source of helium in zircons. It's called radioactivity. And a huge number of heavy elements have alpha decay in their decay chain. It's one of the most common forms of nuclear decay out there.
Yeah, and zircons are specifically, so a zircon is really special in its crystal structure, right? So it is zirconium, yep, and bound to oxygen, right? And what's cool is that the zirconium has the same valence as uranium. So uranium can slip in and replace the zirconium, right? So uranium forms an impurity in this zircon crystal. But lead specifically cannot. Lead is chemically, it's chemically the wrong valence. You can think of it as the wrong shape. It's a square peg and a round hole, and uranium is the round peg.
And yet we find lead in there. Why?
Yeah.
Uranium lead decay. And I wonder, in the decay chain from uranium, I believe it's 235, right?
235 and 238.
But we're primarily concerned with one. Anyway, in the decay chain from uranium to lead, I'm pretty sure there's more than a few alpha particles that get emitted.
Oh, yeah, absolutely. There's 5 or 6 in that chain because uranium, I don't know the whole chain off the top of my head, but you hit thorium, you hit polonium, you hit radium, all of those alpha.
Actually, I think you hit polonium like twice.
Do you?
I think you do.
Okay. But yeah, so so uranium 238, sorry, I'm going to come back to this. David, the moon has a lot of helium-3. Helium-3 is rare on Earth. The difference between helium and helium-3 is, as Deadly Dapper said, it is one fewer neutron. So helium, as we think of it, would actually be like helium-4 because it's 4 things in the nucleus, 2 protons and 2 neutrons. So helium-3 still has 2 protons, but only 1 neutron. Cool. Yeah, perfect. So uranium-238, its full decay chain to lead-206 is 4.5 billion years. Uranium-235, its full decay chain to lead-207 is 1.5 billion years. So uranium-238 is overwhelmingly, if you went out into your backyard and you dug up uranium, almost all of it is uranium-238. There's a little bit of 235. But those are the 2 most abundant natural isotopes of uranium. And
one of the nice things is, when it comes to radiometric dating, if you really want to be very careful, you can check how much of the various decay chain products are in your crystal, because it's not just uranium turns into lead overnight. It goes through several different nuclei or nuclides or whatever you want to call them, of different elements, and you can check all of them. because most of them shouldn't be forming inside a zircon natively.
Absolutely. I'm actually looking to pull up a picture of uranium's decay chain. Oh, this is a nice picture. Let's take a look at you. Here we go. Okay. Bam. Okay. Oh my gosh, this is such a great picture. Okay. I've got to switch what I'm sharing. So we can take a look and really explain what Matt is confusing here. Because what he's not realizing is that helium is emitted frequently throughout time by the same atom. Multiple helium atoms, multiple alpha particles are emitted by the same original uranium atom. And even if that zircon formed 4 billion years ago, it can still, the uranium in it, or what might now be, say, polonium, can still emit an alpha particle tomorrow.
Yeah. So I want to point out that every time you see a little alpha on that screen, that's a potential place for helium to enter the zircon.
Mm-hmm.
So, I mean, in any one chain, you've got at least, 1, 2, 3, 4, 5, about 6 or 7 different times when, of necessity, a helium nucleus is released into the crystal. So if you're checking for helium in any zircon that still has any uranium, which is going to, because remember, we're talking a decay chain that has a half-life of about 4.5 billion years for 238. Yeah, you're going to expect helium to be constantly generated within that crystal.
Yeah.
And so when should you expect no helium? 15, 20 billion years maybe? That might be a reasonable amount of time to get no helium in a zircon.
Yeah. So just a quick note, I'm going to let you guys just kind of look at this, and I think Dapper and I will keep chatting about uranium decay chains. But the way to read it is you really just follow the arrows. So this is uranium alpha decays to thorium, which then beta minus decays to, I don't actually know what PA stands for. And then that beta minus decays to, this is uranium-234, which alpha decays to a different isotope of thorium, alpha decays to radium, alpha decays, I don't know that symbol off the top of my head, alpha decays to polonium. Polonium can then either alpha or
PA is protactinium.
Protactinium. I feel like I don't.
That's one of those elements that
not knowing that one.
Yeah, that's one of those elements. Is like, was that? And it's like, don't worry about it. It doesn't really exist in nature very much. So and then we're going to.
And notice protactinium. It has a half-life of minutes, right? So once we hit protactinium, it's like almost immediately is gonna beta minus decay.
Yeah, look, the reason that no one knows about protactinium is because it's basically impossible to get any like substantial like sample of it. It barely exists. But yeah. And then I will point out that the in some places we get some branching areas, and the dotted area is the less likely but possible chain.
Exactly, because there's multiple. So like uranium-238 can actually, like, its less likely form of spontaneous decay is spontaneous fission. So it can just fission if it wants, but that's much less common than the alpha decay.
Yeah. And you got to realize that when we're talking about these things, we're doing like quantum physics, basically. This is all governed by the sort of stochastic probability-based thing. That's why we have a half-life rather than like a linear rate. And it's why there are, well, maybe it'll go this way, maybe it'll go that way. Who knows?
Right. And we can talk about these things in terms of probabilities and all of that, but we're generally talking about probabilities. So Dapper, there's a great question in the chat from Scott Duke, which is a little off topic, but only a little bit off topic. Are you familiar with the natural occurring nuclear reactor in Africa?
The Oklo? Oh, I think it's Oklo reactor. I said Oklo, and I'm like, no, that sounds wrong. But yes, I am. So one of the interesting things about that is that it basically precludes young Earth, because you can look at it and say, okay, so we know that this is a nuclear reactor that is inducing fission in, fissile material in the Earth's crust.
Thank you, creation myths.
Of course. And so the thing is, fission products are very distinct, right? They don't look like decay chain products. So if you look up, or if you take samples and you check to see, okay, how much fissile material do we have versus how many decay products versus how many fission products, you can get an extremely good and basically impossible to counter estimate as to how long this reactor has been running. And guess what? It's been running way longer than creationists say the Earth has been around. And by way longer, I mean many orders of magnitude.
Yeah. So, team, there's a region in Africa, Oklo, where think of it as you could have made a uranium mine there, right? There was a high concentration of uranium, right? It was a good place to dig that up. But when people looked, the isotope ratios were wrong, right? Basically, there wasn't enough 235, I think is what it would have had to have been. And so what they figured out was that the uranium in this place sustained nuclear reaction. It was a naturally occurring fission nuclear reactor, which just blows my mind.
Right, that is completely mind-boggling.
It's completely mind-boggling.
Because it's not easy to get a nuclear reactor working.
No, so what you need, if you're going to do it with naturally occurring uranium isotopes, right? You need heavy water, generally, because that's how CANDU reactors, Canadian deuterium reactors, work. So it's very cool. So basically, you had to have just the exact right conditions of water flowing through this uranium, right? And that water, what it does is when the uranium fissions, it produces neutrons, but those neutrons are running around really fast, and it's unlikely that they're going to hit another uranium atom to then induce fission to sort of continue this decay, this chain. So it's a chain reaction, right? And to have it sustained, you need one neutron from every one fission to go on and cause another fission.
But are they fast or are they high energy?
Yes.
I'm just pointing at the scales involved. Speed is a little ill-defined. That's
true. That's fair. So anyway, so I don't quite know. So I don't know exactly the physics of what was going on, but somehow you had to get basically heavy water, I think. So David, that's a good point. Stars are natural fusion reactors.
Right.
We are talking about a naturally occurring fission reactor. Yeah. And as far as we know, this is the only place it's ever happened on Earth, right? Yeah. Because it's just all of the stars had to align just right to get everything to go, and it's so cool.
Somewhat ironically, it's much easier for humans to make fission reactors than fusion reactors, but it's much easier for nature to make fusion reactors than fission reactors. Mm-hmm. So it's a little weird that way, because it's fission reactors, naturally, they're a dime a dozen. There's trillions of them.
Yeah.
They're all over the place.
Did you ever read the book, The Radioactive Boy Scout?
Oh, is that about the kid who built a technically working nuclear reactor in his garage as a Boy Scout project?
Yep.
Yeah, don't do that, guys. That's a bad idea.
But
you can do it. A kid in his garage can do it with access to, was it radium he was using? Because he could find it in paint or something?
Yeah, he was using radium.
But which is not what commercial reactors typically use.
He built a neutron gun. And he had
super dangerous.
A little bit. Yeah, neutron radiation team, that'll kill you so fast. Yeah. That's the scariest form of radiation. And Don Giovanni, absolutely. So most uranium reactors use regular water, but they enrich the amount of uranium-235. So that's an enriched reactor. So all uranium fission reactors, so all fission reactors in the US work like that. So they have enriched their uranium to be about 3% uranium-235. Weapons grade is enriched over 90%, just so people
Which
know.
is not easy to do.
Yeah, that's not easy to do. That's very expensive.
The thing about different isotopes is they really only differ in terms of mass and their nuclear decay chains. But you can't separate things by nuclear decay chain because you need them to still be the thing that they are if you're trying to get a hold of them. And so the only way you can do it is you have to find ways to sift them by mass. And so what's typically done is basically you just spin samples at absurdly high RPM. And then the heavier things go farther to the outside and the lighter things stay closer to the inside. And you skim that inside stuff off and you spin it again.
Mm-hmm. So you got to keep spinning. And so you're forcing that uranium-238. You're separating them by mass.
Yeah.
There's a great book that's called The Girls of Atomic City. There was this town in Tennessee that was like made by the government in World War II. And that's where they enriched uranium. And because it was wartime, it was almost completely women that were doing this work. It was kind of cool to read. Okay, so hopefully we all have a good understanding of how these decay chains work. That like, if you were to hold a zircon in your hand, it could be making a helium atom right that second, even if that zircon was made several billion years ago. Because
there's actually a pretty decent chance it is.
Yeah, absolutely.
Wait, speaking of neutron radiation, though, I heard a neutron once.
What? Sorry?
I heard a neutron once. I was
heard a neutron once. How did you do that?
So in training, I had one of our, radiation detectors, and I had it on the setting for neutron radiation because we were doing. The thing is, usually when you're checking for neutron radiation in a nuclear reactor, you don't get any neutron radiation because they're very heavily shielded. But of course, again, it's all quantum mechanics and stuff, so there's always a chance that a neutron will simply find a free path through all of the shielding and will hit your detector. But it's like, most of the time, like, you can go months and months of monitoring for neutrons and never have a single detector hit in a reasonably well-shielded reactor. But what do you know? I got a hit. And my instructor was all like, no, you didn't. I was like, I mean, look at it. The deal just popped up. What do you want from me?
Yeah.
And he's like, oh my God, it did. It's like, yep, I heard a neutron once.
That's nuts. I got to go tour when I was an instructor in a PTC, right? I went down to prototype and they were shut down at the time. So like we got to go into the actual I got to like hug the reactor, right?
I've sat on top of reactors.
Yeah. So what I'm saying is that I don't care that like my radiation detector, like I know it's picking stuff up. I'll go hug this reactor. That doesn't freak me out at all. But you're like one neutron, and I'm like, oh my gosh, like that makes me nervous.
Yeah. Like
one neutron, not really, but like neutron radiation scares me so much more than any other form.
Oh, it's horrifying. I mean, I remember I was an electrician, so one of the things that we were in charge of was changing out all the lighting stuff in the reactor compartment, which is not a big deal. I mean, it's like a 5-minute trip in there. But the thing is, you hear about neutron embrittlement, which is where neutrons fly in and just break down all sorts of like chemical bonds and change nuclear, what element is in there, and so you would get these, especially the starters, right, which are these little plastic things, and they're basically capacitors. And it's a little bit complicated, but basically, in order to turn on a fluorescent light bulb, you need to have a really high amount of voltage initially. Okay. And they're what provides you with that. Okay. So, but when you would take them out, the plastic surrounding the capacitor would just crumble into a weird dust because of neutron embrittlement. And this is after like a few months of being in the reactor compartment. The plastic is just turning into dust.
Ooh.
Yeah, which, by the way, technically radioactive dust, but yeah.
That would freak me out every time.
Yeah, it's crazy.
By the way, I'm channeling Erica tonight with my hard seltzer.
Nice.
This is coconut pineapple. That's not half bad. Yeah, that sounds terrifying.
Look, I know how to stay safe from radiation, and right, things are very well shielded. But when you realize what happens unshielded, it can be pretty arresting and like, oh, hey, this is to be respected. Don't necessarily be afraid of it if you know what you're doing and everything's proper. But like, yeah, don't take risks when it comes to nuclear reactors. Just don't do it.
Right. Yeah, Titan, absolutely. Radium, I would hold radium in my hand all day long, right? Because it's an alpha emitter, and your skin is going to protect you from alpha particles. And even the gamma radiation that comes off of it, radium famously glows green, right? So that means that the gammas coming off of that radium is in the visible range. It's non-ionizing radiation. Right. It's not dangerous.
Very low energy.
Right. I would hold radium in my hand all day long, but like, don't breathe it, don't eat it, because the second you get an alpha emitter inside your body, so bad.
Have you heard about the people who used to paint on the glow-in-the-dark numbers on watches?
Girls, where they would lick the paintbrush and their whole jaws fell off.
Yeah. And the thing is, as someone who paints sometimes, I know that, licking a paintbrush is a really good way to restore, the tip to a paintbrush. But when you're painting with radium paint, maybe don't do that.
Maybe don't do that.
Yeah. Don't. Oh, God. All right. We need to move on before this just becomes a morbid discussion about all the horrible things that radiation can do to you.
Yeah. By the way, Dapper, I want to watch. What do I want to watch? What's that movie? I think it's got. Is it Hunt for the Red October? It's a submarine movie where everybody dies from radiation.
No, it's not Hunt for Red October, then.
It's not Hunt for Red October.
Yeah, because that's like most people live in that one.
Yeah, this is like something the Widowmaker, and it's about like a Russian sub, and I watched it when I was way too young. Anyway, well, never mind. Okay, zircons. That's what we're still talking about over here. Yep,
we're still there.
After 4.5 billion years, and it's supposedly the oldest crust of the Earth, the oldest rock. Folks, what a joke. And here's the thing, too. If I was to go into a garage where we have an air compressor, and you know how the air compressor has to kick on to recharge every once in a while, the air cannot stay compressed in there over time.
That's
so the
true.
more time that the air sits in the air compressor, the more it's going to have to recharge because the air will slip out. Well, same thing with rock crystals. It cannot be there from billions of years ago.
Okay, hold on. Pause this for a second. I love this because the compressor kicking on is the direct analogy for further nuclear decay releasing more alpha particles.
Exactly.
You're right, Matt. You're right. It couldn't stay that way. But we have an air pump that keeps pumping in alpha particles.
Exactly. So I think based off of what he said in this, I think he thinks that all of the helium produced by the radioactive decay was produced all at once when the zircon formed, right? That's what I think he thinks is going on. But that's just not what's happening.
Right. It seems like he thinks that all of the helium is primordial, which, spoiler alerts, basically none of it is.
Right. Yeah, effectively none.
Yeah. Okay. I mean, can I say for certain that there wasn't a single helium atom trapped in? No. But basically, you can essentially ignore any primordial helium.
Yeah.
Rock. And there wouldn't be any helium inside of these rock crystals. And so just as in a garage in an air compressor, you have air that slips out over time, helium slips out of rock over time. Nobody would ever say that the compressed air has been sitting in an air compressor for billions of years.
Unless you had a billions of year old compressor that kept pumping new air in.
Exactly.
Like he's so close to having an analogy that actually works and explains the phenomenon. Mm-hmm. But nope. He just
close but no cigar there, my friend.
I feel like Matt's one of those no drinking, no tobacco guys, though. I don't think.
I'm absolutely positive.
Also, Matt, I like that you started filming at the golden hour, but like you got to turn so the sunset is in your face. so that you're not backlit. This is just a cinematography tip for Matt Powell in the future. If he ever watches this, the golden hour is great, but you got to put your face towards the sunset. That's the key there. I'll be honest, backlit video is one of my pet peeves because it's so easy not to be backlit.
Yeah. Okay.
Nobody would ever say that helium inside of rock crystals has been sitting there for 4.5 billion years.
You're correct. No one says that.
Oh my goodness.
Honey.
Remember when you were like, oh, we can get through 4 of these?
Yeah.
Oh my goodness. Matt Powell is... You know what? I kind of do hope that he moves down to Alabama and lives in Dinosaur Adventureland, because I couldn't think of any 2 people who were better made for each other than Matt Powell and Ken Hovind. Maybe Matt Powell can become Mrs. Hovind number 5 when Mrs. Hovind number 4 inevitably leaves.
Okay, there's like 40 seconds, and I think he's made all the points he's going to make.
Yeah, we're going to just get to
Nobody
preaching,
would ever
maybe.
say that unless they're just ignorant of the facts. And that's what this channel is about. It's making sure that you know what the facts are.
Oh, honey, no. Honey. Oh, no. I think this is going to shill. Okay, nope, we're done with that. Let's pop back and grab another one. There we go. We need something new. Do you want to listen to them talk about comets, stars and comets?
I kind of do. I mean, I like stars and comets just
Plus, we're back to our Russian mafia tracksuit.
Maybe he'll make us an offer about stars and comets that we just can't refuse.
It would be Italian.
Hey, you know what? Italians like their tracksuits too. I think it's just an organized crime thing. Like, now that I'm thinking about it, like, I can picture like some low-level Yakuza enforcers hanging out in tracksuits, but not like the bosses. They're all going to be in nice, like, business attire.
Okay. All right. Here we go. We've got, hey guys, it's Matt Powell here.
So one of the things that people point to oftentimes for proof of evolution is actually the solar system. And they'll say that the solar system proves that the Earth...
So when he says evolution, he just means
science.
He just means science. He just means that, like, the universe is old. It's because you would never point to the solar system to explain insert favorite,
like, biodiversity.
Biodiversity fact here, right?
I mean, except in the rare interfaces like, you know, asteroid impacts, then okay, sure. But generally speaking, the solar system could be arranged in just about any different configuration you can come up with, as long as it doesn't preclude life from being on Earth. Right. And evolution is A-okay with it.
Exactly. It doesn't really care. I guess there is the field of, like, astrobiology, which may be the weird small intersection. But...
Well, that's primarily about how life can form and exist outside of Earth, which, again, any solar system configuration that doesn't preclude life, actually any solar system configuration, even if it precluded life on Earth, would leave open the possibility of life outside of Earth. So there is no way for the solar system to even affect astrobiology. There's actually less of a way for it to affect astrobiology than just the rest of biology, because at the very least, you have to have a solar system that isn't basically just a bunch of chaotic nonsense with everything impacting into everything else. Because, that might preclude life. Right. But as long as we have a stable orbit for Earth and reasonable temperatures, Earth doesn't care about what else is happening in the solar system, basically.
True.
It is 4.5 billion years old. But what I find interesting is if you actually look at the solar system and comets and stars in particular, you'll actually see that this idea that it's 4.5 billion years old is completely bogus.
He said if you look at the solar system, and comets and stars in particular, does Matt Powell think that the other stars in the universe are inside the solar system? Because this is the guy who Okay, but this is the guy who thought that the sun burned because it was burning through air that was in space. And sure, it was different than air on Earth, but like, this is the guy who thought that the sun was basically a coal fire in space. So this man has like 1700s level understanding of science.
Fair. So okay, so I guess I can't.
He might actually think that the stars are part of the solar system.
He might. Because certainly the stars are older than 4.5. Not our sun is.
Well, some of them are. Some of them are younger.
Fair. Yeah. Okay.
I think he might think that, which is kind of horrifying, but
that is kind of the adventure of these videos, is trying to figure out how Matt thinks the universe works.
Yeah. Look, it's hard to underestimate Matt.
It's true. That's true. Okay. Let's see what we got.
Just complete nonsense.
Is it?
And the reason that we know that is because stars actually die. They blow up about 1 per 25 years per galaxy. So we actually only find about 200 dead stars in our galaxy. And so what that proves is that our galaxy, the Milky Way, is less than 10,000 years old.
Okay, so I don't know if Matt knows this, but fruit flies only have a lifespan of 1 day, which means that overall, you generally get a death in fruit fly population equal to the fruit fly population of adults per day. So let's say you have a very conservative estimate of a few billion fruit flies alive right now.
Mm-hmm.
That means every day, 2 billion of them should die. Mm-hmm. Now, if the Earth is 6,000 years old, we're going to do some math here. This is going to be great, right? So the Earth is 6,000 years old. So that is times 365.25. All right, so that is 2,191,500 days old. And we'll just go with there are a billion adult fruit flies at any given time. So that's 1,000, a million, billion. So why don't we find everywhere on Earth a carpet that consists in its entirety of 2 times 10 to the 14th fruit fly corpses? Oh, you think maybe it's because fruit fly corpses don't last forever, just like stellar remnants aren't detectable for the entire history of the universe? Maybe. Maybe things don't last forever after they form. Stars included and stellar remnants, because the thing is, when you see a stellar remnant, it's primarily because it's one of a few things. There's a planetary nebula, which you can see for a few hundred, maybe a few thousand years, or you can actually directly detect the stellar remnant. But the problem with that is most stellar remnants are faint, especially if their magnetic pole isn't pointing towards Earth in the case of neutron stars. So in the case of white dwarfs, they're very faint because while they have a fairly bright, like if you were standing right next to it, they'd be fairly bright. Their residual energy is actually not that high. They're hard to find. Neutron stars, you basically can't find them unless you would detect them gravitationally, or at least one of their magnetic poles is sweeping over Earth periodically, in which case it's a pulsar. For black holes, you basically can't detect them unless you detect things that are orbiting them that are shedding more light. So most of them are probably more or less invisible. And if you're looking at distant galaxies, it becomes even more problematic, because if you're looking at, say, a white dwarf, it's hard to tell the difference between a white dwarf, which is basically emitting a black body spectrum, from another star that's also basically emitting a black body spectrum. Now you can check for things like, emission spectra and see, a white dwarf should have a cleaner black body spectrum than most main sequence stars. But what if this is being interrupted by, say, lots of dust and gas? And then you can try to filter out the absorption spectra, but you're not going to be 100% accurate on this. So stellar remnants are just not easy to detect thousands to millions of years after the initial star goes nova.
Yeah. So is what he said, because I was trying to follow his argument, and I wasn't being very successful in following his argument.
His argument is, sorry.
So I think what he was trying to say was, and I mean, I don't know if we should I don't know that number. I don't know the number of how frequently does a star die, right?
I'm willing to say every 25 years, somewhere in the universe, a star goes nova. Like, fine, sure. There's a lot of stars out there.
Yeah, like there's a lot of stars. So like I don't even so I'm not going to contest that number, because I just don't know it. So
I neither know it nor does it seem like off the wall crazy. Like that seems like a perfectly reasonable number.
Yeah. So because I thought he said we see some number of stars in our galaxy now, therefore the galaxy can only be 10,000 years old. And it just that logic doesn't.
Well, I think his logic is we should see more stellar remnants because more stars should have died over the course of 4.5 billion years than the number of stellar remnants we can see.
Let's back it up because he never says the phrase stellar remnants. So let's
I don't
see
think
what
he knows that
actually.
phrase.
Well, that's fair. But let's see what he actually says. Let's try to actually parse this out.
Our galaxy. And so what that proves is
No. Back a few more seconds. Okay.
25 years per galaxy.
20. So inside our galaxy, he's saying that a star would not even go supernova, but a star would die once every 25 years because not all stars go supernova, right?
So the way he's giving it, like per galaxy, is a weird metric. So I'm not sure exactly what he means by that.
Okay. I think what he means is in a given galaxy, but
that wouldn't follow because galaxies vary greatly in number of stars.
Yeah. So
Andromeda, which is considerably bigger than Milky Way, is going to have a whole lot more stars go nova per unit time than, say, the Small Magellanic Cloud, which is tiny.
Right. And I'm even thinking of if he's thinking that all stars die by going nova, like that, then different galaxies have different concentrations of different stars. So that's all really messed up. Okay. All right. So it's a weird unit, but I think fundamentally what he's trying to say is that in our galaxy, you should see one star die every 25 years. I think that's his claim.
I think so.
Okay. Okay.
So we actually only find about 200 dead stars in our galaxy.
Oh, okay. So he does. Yeah. He is thinking stellar remnants. We can only. Okay. Yeah. So you had it on point. That's his argument. His argument is we don't find enough dead stars, therefore it's only 10,000 years old, which is silly because dead stars are hard to find. They don't glow anymore.
Right. Or they do, but in ways that still make it hard to figure out exactly what's going on and where they are.
Exactly. Sorry, I was being a little, I guess, pedantic. Okay. All right.
I'd also point out that if he says that there are 200 stellar remnants in the galaxy and there should be 25 times the age of the Earth, that means that we're falling 1,000 years short.
Right. Also, the other thing there is that the age of the galaxy is not the same as the age of the Earth.
That's also true.
Right. So that's the galaxy is older than our solar system, other stars. Anywho, in case people were wondering. Okay. So he's making a lot of assumptions in here, and so far none of them seem good. Yeah. Okay. All right. Let's see.
Of dead stars in the galaxy, but since there's less than 200 and only one per 25 years dies, that literally proves beyond any shadow of doubt.
No, it doesn't. It's this is really just if you went out, right, and if you went out into a field and all you could find were 12 bananas, right? That doesn't mean that beyond a shadow of a doubt there are no other bananas. So you know what I mean?
Right. It's the whole thing is crazy.
Yeah, or maybe golf balls is a better example, right? Because people lose golf balls left and right, right? So you lose 5 golf balls every time you play a game, and you're real good at finding your golf balls, right? So you always find them. But you can't figure out how many people have played golf by the number of golf balls on the field, on the green. There we go. That seems like a golf term. There we go.
It is a green. Oh, also, by the way, apparently scientists know of about 2,000 pulsars, which means that's 2,000 stars of sufficient size, or sufficient mass, I should say, to collapse into neutron stars. Mm-hmm. And we know that pulsars are only a fraction of the actual neutron stars that exist, because most neutron stars are going to collapse in a way that neither of their magnetic poles is going to actually directly point at Earth. Which means when Matt Powell says that we only know about 200 stellar remnants, he is either grossly misinformed or lying.
Mm-hmm. Yeah. Okay, let's see what he has to say about comets.
That our solar system is young just based on star deaths.
No.
And so comets also are deteriorating over time, short period ones in particular.
Cool.
They orbit the sun every 200 years, and they burn up.
Not every single comet.
No, they have a wide range of orbital periods.
Yeah, and
so
also the Oort cloud exists.
Right. The way that a short period comet forms, right, is the Oort cloud bodies have fairly low. Now I'm having trouble thinking of words.
Okay, hold on, Dapper. I'm going to explain what the Oort cloud is.
Yeah, okay.
And so gather your thoughts on that. So, hi team. We have a solar system. In our solar system, there's the star, there's the planets, then there's the Kuiper belt, which is like rocky and icy bodies that like Pluto is a part of. That's like outside the orbit of Neptune, right? And that's like leftover planetesimals and bits that didn't get formed in the planets. And then outside the Kuiper belt is the Oort cloud, which is this like group of comets, basically, that is orbiting the sun with just its radius is it's really far away. It is a very high eccentricity. It's a very elliptical orbit because it's really far.
Well, that's actually one thing is the bodies that are stably in the Oort cloud actually have fairly low eccentricity orbits. But what happens is short period comets will undergo gravitational interactions with other members of this body of comets, right? And one of the things is that just from a statistical basis, it's essentially impossible for a gravitational interaction like that in a long-standing body of orbiting things to end up kicking something entirely out of the solar system. And even if it did, well, we're not going to see it. What's more likely is that it's actually going to kick down the perihelion to a very low point in the solar system. And then further interactions are more likely to kick the perihelion lower than they are to raise it or to raise the aphelion. And perihelion is when you're closest to the sun, aphelion is when you're farthest from it. So depending on how low your perihelion goes after these gravitational interactions, that's going to determine your periodicity, because it's going to change the mean radius of your orbit, which is just the average distance you are from the center of mass that you're orbiting, which in this case is the sun. So the lower that goes, the shorter the period is. And they're not all 200 years. Some of them are shorter, some of them are much longer. But the curious thing is, when you calculate the aphelion of all of these comets, it tends to come out to a relatively narrow range that's really far out there, where the Oort cloud is. Weird. Because if the most likely gravitational interaction is that your aphelion stays about the same and your perihelion is kicked to a much lower level, well, guess what? If you add up all those aphelions, you're going to get a radius around the sun that's going to be where the Oort cloud should be. And it is true, as I suspect Matt's going to point out, that we don't have direct observations of things orbiting in the Oort cloud. But the thing is, we don't really expect to. However, the fact that statistically speaking, we have an unusual number of comets that have aphelions at within a certain range of radii of the sun. It's very hard to come up with an explanation for that other than the Oort cloud existing.
Complete quick tangent. One of my favorite undergrad semester project that I ever had was I was taking it was 12-4-20, which is physics. Yeah, I know, right? Yeah. No, it's the class is called Physics and Chemistry of the Solar System, right? It was very fun. And what we had to do, so the goal was to like teach us how to do proper research papers and stuff like that. That's a very common undergraduate project for science classes, right? But what the professor had us do was pick a topic in planetary science that had been disproved, right, or was no longer accepted, but there was like real literature debating it, and just sort of present a review paper on this topic. It was super fun. And so what I got to do was the Nemesis Hypothesis. So the Nemesis Hypothesis, was that, so what there was, for a period of time, people thought that there was evidence of periodic mass extinctions. So Right. So that mass extinctions were happening every however many million years, right? So that these were happening with a specific frequency. And then they were like, well, we know that like there was the big dinosaur extinction from the KT extinction, right, with the asteroid impact and all that. Yeah. And so maybe all of these mass extinctions that there's actually not evidence for in the rock record, like that was changed, right? New evidence came and they corrected that. But for a while, they thought there were these periodic mass extinctions. So it was like, well, what could cause asteroids or comets to come in to the inner solar system and impact the Earth periodically? So the thought was that we were secretly in a binary star system where the second star was like a brown dwarf that they named Nemesis that you couldn't see, right? Because it was so dim. And it would, every like 26 million years, careen through the Oort cloud and send a bunch of comets spiraling into the inner solar system. And it was just a wacky theory.
I mean, it fit the data that they thought they had.
Exactly, yeah. So that was and then, the data updated to not need an explanation. So Nemesis Hypothesis died out. But it was a very fun thing to like research and look into.
By the way, there is a quite good Isaac Asimov book by the name Nemesis, which is about a star that's going to make its close approach to the solar system, which is going to cause a lot of problems. And so if you like classic sci-fi, check out Nemesis. It's one of Isaac Asimov's few books that don't involve robots, although he then later folded it into his robot continuity through this Foundation series because, spoiler alerts for like, half century plus old books, all of the Isaac Asimov books end up taking place in the same universe.
Gotcha. Okay. Sorry. Okay. So Matt Powell was trying to explain comets, and he thinks they all have a 200-year period. No.
For some reason.
For some reason. Okay.
3 to 5% each orbit. And so they can't be here from more than 10,000 years ago because they would have burnt up by now. And so short period.
I mean, there's more variation in short period comets than this, but like these aren't completely like wackadoo crazy numbers to give as like averages. I don't like the way he's phrasing it, but if he were to say like on average about, then I would say, yeah, sure, these are fine. So once we have the caveat that these are not hard and fast numbers for all short period comets, and in fact they're approximations of averages, then that's an okay statement to make. Yeah.
Well, and the other thing that's important though is that like you can have a long period comet that like through gravitational interactions becomes a short period comet.
Ultimately, that's how we get short period comets.
Yeah, that's how we get short period comets. So what's interesting to me is that in both of these videos, his fundamental misunderstanding, right, is in thinking that sort of everything gets, because it seems like he really just thinks that everything gets set in motion and then nothing changes.
Yeah.
Right? It's the same. So like all comets have to already be orbiting, and so they can't have changed, right?
Which is a bizarre way to go about things because like things change, right? We know that things don't stay the same. And processes that happen, like even if there is a process that takes a certain amount of time and then it completes, it doesn't mean that all of those processes started at the same time. It's bizarre. But it's basically the same argument as saying like, oh, I have a zit on my butt that formed a week ago, so I guess I'm only a week old. No, that's not how things work.
Right. That's really not how things work. And I think what, honestly, this thought process he has is rooted in is I think the way he thinks about the universe is from that creationism standpoint, which is sort of God set everything up and then let go, right? And so then everything just sort of ran forward from that initial setup, but like you can't change anything. Do you know what I mean? Like I think that's kind of the mindset that we're seeing, and so he's not understanding that like you get a short period comet because it used to be a long period comet.
Right.
You get more helium because the the uranium is alpha decaying over a long period of time.
Right. That's it does seem like he thinks of the world as like a physics simulation that you set up in your computer and then it runs and then that's it.
And that's it. Like everything's sort of fixed and you can't touch it. And Scott, to answer your question, how much of Powell's script is basic Hovind material as far as comets are concerned? I actually don't know. I've never heard Hovind talk about comets.
Well, you may not be surprised, but I do know about how much of it is recycled Hovind material, and it's a very high portion of it. It's almost all a combination of Hovind talking points with taking the dumbest possible take on pop sci articles that he comes across. So that's really the only novelty with Matt Powell. And this is, in fact, a Hovind argument that he is recycling. It's not one of Hovind's big talking points. And really the only reason I know about it is because I do a weekly show where I drunkenly debunk Kent Hovind. If it were not for that, I would not know. Because, I mean, look, when I was a kid, I liked Kent Hovind because I was a young Earth creationist. But, like, as an adult, I wouldn't know this much about Kent Hovind if it weren't for the fact that every single week for not quite every single week, but virtually every week for over a year now, I've been doing a weekly 2-hour show about Kent Hovind, which is mostly just an excuse to, hang out with my audience and drink a bit.
Yeah. You mean also, like this live stream?
Well, I mean, I'm not saying there is whiskey in this glass. I'm also not saying there isn't whiskey in this glass. Yeah.
Okay. How do we're not even halfway through this video, and I thought he's hit his 2 points. Okay.
Welcome to Matt Powell.
Let's see what else he's got to say.
Comets literally prove that the solar system is young as well.
They do not.
Stars and comets both prove that the solar system is not billions of years old.
False.
And that you were lied to when somebody came to you and said that the Earth was billions of years old, or the solar system was billions of years old, and that evolution was somehow a fact. Folks, if evolution were true, there would be hundreds of thousands of dead stars in our galaxy and in other galaxies. But when we look at other galaxies,
pause it for a second. There almost certainly are.
Yeah.
Right? Like, you cannot base the total number of objects in a class based entirely on the ones that you found, especially if they're a relatively tricky to find class of objects. Right?
Yeah.
So, I mean, you can compare it to when people make population estimates for wild animals, right? So if you wanted to estimate how many rabbits are in North America, you couldn't possibly find every single one. It would be completely impossible. What you can do is you can pick out certain areas and do a survey of that area. And you can say, okay, in this area, I'm pretty sure that there are 300 rabbits. And you can pick a few areas that are representative of like different environments or whatever. And then you can try to make really good informed projections from that. Like, okay, I found 500 in this kind of patch of forest. I found 300 in this little arid area. I found 4,000 in this little area with lots of farmland. And then you can figure out, okay, how much area do those environments take up? Then you can weight the average numbers based on that area. And then you can come up with an estimate as to how many rabbits are in North America. It's similar with stellar remnants. You can say, okay, I can look between, say, spiral arms where I expect to find older stars and more stellar remnants. And then I can look between inside stellar arms where I expect to see more young stars and relatively fewer stellar remnants. And then I can come up with estimates as to how many should actually exist. But you're never going to find them all. It's completely impossible. Right. It's an off-the-wall, crazy expectation.
Yeah. Yeah. That's, because again, finding these are difficult. You can't just like point your telescope at the sky and look, right? Like it's a lot harder than that.
Look, I have seen a white dwarf, but it took the largest telescope available to public use in the entire world to see it as a barely perceptible pinprick.
And that you had to already know where it was.
Well, I didn't. The operator had to.
Yes, excuse me. The operator had to already know where it was.
Yeah,
so that's the really hard thing about astronomy that people don't always think about is like, yeah, it's kind of easy to find Saturn because we know where Saturn is, right? You can look that up.
But if you don't have the available information as to where it is, if you just try to point your telescope into the sky and find anything, good luck.
Good luck. Yeah.
It's not easy to do. Chances are you're just going to be pointing at nothing. At least nothing that you can see with your particular telescope.
Yeah.
Also, that telescope looking at the moon was really kind of blinding. I looked away and I couldn't see anything for quite a while.
Yeah, the moon is super bright, especially in a telescope.
Oh, and this was a telescope that was like something crazy, like 40 centimeters across.
Oh, wow.
Yeah. It's actually not far from where I am. It's Now I'm like partially doxing myself, but yeah, not. I mean, it's a few hours, right? But within a drive, there is the largest telescope available to the public.
Oh, that's super cool.
Yeah, and that's in the world, not like the U.S.
That's very cool. So Dapper knows this, but for all of you guys, by the way, I won't have a live stream next week because I'm going to be in South Carolina because my nephew is turning 4.
Yay!
And we had to get him all the nerdy science toys. So I found him because he needed to call me the other day to tell me that Saturn has rings and some of the rings are made of ice. He is turning 4 and he wanted to call me to talk about Saturn.
That's so awesome.
I got him this. It's we can make a little planetarium in a blanket fort in his room, and you can like change a slide thing so it'll like project Saturn or project the moon. And I'm super excited to build a blanket fort with a 4-year-old to make an indoor planetarium.
That does sound really cool. I'm not gonna lie.
It's gonna be super fun. Don't worry, team. We also got him. He's very into Transformers, so we got him age-appropriate Transformers. My husband's very excited about this. So maybe we should take Matt to a planetarium. Matt, I would take you to a planetarium. Like, I really would, Guy.
Planetaria is it planetaria or planetariums?
I don't know.
We're gonna go with planetaria because the Latin.
Yeah.
Planetaria are pretty cool. It's, I mean, there's something to be said for the fact of actually going out and looking through a telescope at the actual photons that left whatever the object is, however long ago, and they're now hitting your eye. But on the other hand, you can do things in a planetarium that you just couldn't do in a single night looking at the stars. Yeah. Because in a planetarium, you can look at essentially anything as long as they have the files and information in the system for the projector. Mm-hmm. And that is cool on a different level. Yeah. By the way, Silver Harlow makes a super good point that there have to be hundreds of thousands, if not millions, of dead stars to provide all of the heavier than helium in our solar system in the universe. Now, I'm sure Matt Powell's counter would be like, "Oh, I don't think that all the heavy elements came about through nucleosynthesis." He wouldn't say nucleosynthesis because he doesn't know the word. He would say God just created all of these heavy elements in situ. He also wouldn't say in situ. Right. I cannot talk about science as dumb as Matt Powell does because I will automatically say smarter words than he knows. Yeah. Okay. All right. What else do we have here, Matt?
We see that there's only a few hundred dead stars. When we look at our galaxy, only a few hundred dead stars. If one dies per 25 years, it literally proves beyond any shadow of doubt that the galaxy that we are in is a young galaxy. No, honey. And that we didn't have enough time to evolve from an amoeba all the way to humans.
I think that's his whole point. And the thing is,
I'm done with this.
His claim assumes that we have reason to think that we have a nearly complete set of stellar remnants that are in the solar system as known objects, or not solar system, sorry, the galaxy as known objects. Yeah. That is a really bad assumption. We should not make that assumption.
I'm also just going to back up a second. I wouldn't necessarily assume that like stellar death rates are constant. That should be a function of time, right? Because you should have a period in a galaxy, right, when you're making more. So it's a function of time,
but it's not something you could fit a simple formula to.
Right. But that's like
pop zero stars are going to die off very quickly because they tend to be. They probably would have been very high mass, but then when you get to pop 1 stars and pop 2 and pop 3, which is most stars that we have still are 2 or 3, but there are some population 1 stars out there. Yeah. The problem then becomes that it's going to depend on a lot of things, including what's happening in the local galaxy. Has there been like recent galactic mergers? What's the local gravitational thing going on? Things like that. So all of those things are going to change. And right now, this is something you guys should go look up. But most estimates say that we're probably very close to a drop-off in stellar formation. Okay. And in the next few billion years, significantly fewer stars are going to be forming per unit time than were in the previous few billion years.
Yeah. Is that in our galaxy or in the universe?
Well, it's in our galaxy and very nearby ones, which probably means also the universe. But the thing is, because of things like light time travel, it's like, what does it mean for the current state of the universe? You know, a billion light years away. Like, it's not well defined.
Fair. Yeah. So I think our point is, so like Matt's claim here is fundamentally predicated on one that we can see every single dead star, right? That we have, like that just stuck around, right, for us to look at.
Which, by the way, means we shouldn't expect to ever find a new one.
Right. Yeah.
Which we do.
Yeah, and two, that stellar death rate is a constant.
Which it is not.
Right. Which it is not. Yeah.
Over short enough times, you can give a rough measurement. But the thing is, it's like,
and short enough times are in you know, astronomically speaking, the whole of human history, right?
Yeah. The universe has essentially been static for all of human history.
Yeah, because that's another thing that I've noticed younger creationists are really not very good at. And though I will say this is a hard thing of thinking about, okay, what does long mean? What does a long period of time mean?
Yeah, we've had that conversation before.
Yeah.
Because you as someone who's doing like climate and meteorology, when I said that something existed like 30 million years ago, not that long ago, for a climatologist, 30 million years is a really long time.
Yeah.
But for paleontology, it's like, you know, it's whatever.
Exactly. I did appreciate in my debate with Kent when he insisted that 6,000 years was a long time, and I didn't laugh, so I'm proud of myself for that.
You know, that's actually one of his more recent additions, is to start saying that. Like, that hasn't been a thing he's been pushing for a long time, and he didn't say it in my debate, but I don't know if I could have kept a straight face at that, because the thing is, it's a long time in terms of human history, yes.
Yeah.
But in terms of many fields of science, it's essentially zero.
Yeah, it's near indistinguishable from zero. It's in the rounding error, you know?
Yeah, that's true. I mean, you think about things as like, oh, hey, the dinosaurs went extinct 66 million years ago. Well, 6,000 can live very comfortably within that rounding error.
Yeah, absolutely. Because
also, one of the things is the uncertainty that we have there is a few 100,000 years.
Right. Yeah. Okay. We've been going an hour and 20. So we definitely don't have time
half of the videos.
Maybe. Yes, we definitely don't have time to do a third one. Also, I just don't have a third one in me. My brain is rotting.
That's very fair.
So yeah.
Asterix asks, aren't there trees older than 6,000 years? Yes, there are.
Yeah.
There are indeed. There are living organisms older than Matt Powell thinks the universe is.
What are you going to do with that?
If that tree was created before day one, maybe that tree is God.
What?
Well, I mean, God did appear as a burning bush.
Mm-hmm.
So why can't he also be a tree?
Yeah, I don't know. That's a good question. What is the oldest living organism?
That is a difficult question to answer.
Mm-hmm.
So the problem there is there are certain things for which whether or not it's a living organism is actually not easy to figure out. So for instance, we have clonal forests, right? Where essentially every tree trunk of the same species is connected to other parts of the forest of the same species in the root system. And rather than growing from seeds, they tend to grow clonally in what's called vegetative reproduction, where the roots go down horizontally, and then when they're far enough away and in an area where they think there's enough nutrients, they'll send up a new shoot that becomes a trunk. Is that a new organism?
Ooh.
Maybe. You also get similar problems with fungi, where you can have a mycelial network that can extend for miles unbroken, and then it will shoot up occasionally, mushrooms as fruiting bodies here and there. Is that one organism? I mean, the network of filaments is often one single cell thick that's connecting these little clusters that shoot up mushrooms every once in a while. Is that one organism? So if you count things like clonal forests and really large mycelial networks, then the oldest organism is one of these things. And we have things like the Pando Forest in Utah, which is a clonal, I think it's aspen trees. It's a clonal stand of, I think, aspen trees. That's probably somewhere around 40,000 years old, because we have dendrochronology that can correlate these trunks back about 40,000 years. So depending on whether or not you would count a clonal stand of trees as living organisms, we can say, well, maybe 40,000 years. If you want to say an individual trunk is the organism, then we're in like the 10 to 12,000 years range.
Yeah. That's super cool. I knew that I didn't know about clonal forests. That's very cool.
Yeah, look up Pando. It's called Pando, Pando. It's a clonal forest, I believe, in Utah.
Pando.
Not Panda.
Pando, also known as the trembling giant, is a clonal colony of an individual male quaking aspen.
I was right, aspen.
Determined to be a single living organism by identical genetic markers and assumed to have one massive underground root system. It is in the Fish Lake National Forest in Utah. And it is, according to Wikipedia, 80,000 years old.
Man, I underestimated by a lot. So there you go. I consider that to be a lot in most cases. Like if I say to someone like, "Hey, I need 6 eggs," and they hand me 3, that's not okay.
That's fair, but like I don't know, I am a huge fan of order of magnitude thinking.
Fair enough.
And so to me, even though like if we're thinking about my guess, the answer of the question of if
I don't have to add a 0, we're all good.
Yeah. So my guess to the answer to the question of how old is the oldest living organism, my guess was going to be 10,000 years, right? And so when you said like 40 and even that read 80, it's like, yeah, okay, I'm close to right. It's the right order of magnitude.
Fair enough. Yeah, it does depend on the context. Now, when we're talking about creationism, order of magnitude really is the context that matters, because they are usually like 4 to 10 orders of magnitude off. Right.
Yeah. Well, and that's like with a lot of weather stuff, right? Like winds, right? Usually, like 1 mile an hour wind, 1 meter per second wind versus 10 meters second per wind versus 100 meter per second wind. Like that's what matters, right? But if something is 5 meters per second, let's call it 1, right? Because, or if it's 50, call it 10, right? Because if we're thinking about different fundamental behavior of fluid motion, you need those different, or it needs to be that order of magnitude different. But
at least we're within an order of magnitude and not within like outside of like 4 off, which is the typical Cantogan thing.
I like honey, you're 80,000. You barely look a day over 40.
I'm sure Pando appreciates the compliment.
Yeah, Pando, you're keeping it cut. Like you're doing great.
It's definitely got that silver fox thing going. It's an older gentleman of some distinction.
Oh yeah, absolutely. Well, hey team, I think we're going to go ahead and wrap up for the evening. Thank you so much for joining. If you're not somehow subbed to Dapper, as soon as we end, I'm going to add his channel link in the description, but definitely go check him out. You've got a stream tomorrow afternoon, right?
I do. So it's tomorrow at 2 p.m. Pacific. What is that? 5 p.m. Eastern?
Yep.
I'm going to be having a stream where I'm going to be moderating a discussion between Finding Truth and Jackson Wheat and Steve McRae. Finding Truth is going to be making the claim that the study of life leads to belief in God. And Jackson Wheat and Steve McRae, being people who have studied life and come to a different conclusion than that, are going to be assessing the argument. It's not really a debate, but we're going to have an opening statement from Finding Truth, and then it is going to go to an open discussion where they are going to try to tease apart that, and then I'm going to be there really just to make sure that the discussion doesn't become monopolized and doesn't become unruly. And then there's probably going to be a follow-up on my channel. And I do think that's actually just going to push my my regular upload on Thursday, because I don't want to have to do 3 videos on that Thursday, which is probably what it would turn into, because it would be like the stream, then the premiere, then the after show. So instead, I'm probably just going to do the stream. Then if people want to, there's going to be an after show that they can come on my channel for. And it's not going to be completely open. It's going to be people who I have good reason to think will both add to the discussion and who won't do anything to get my channel taken down.
Fair.
So, yeah.
Fair.
So that's the plan for tomorrow. That's going to be a pretty full day of streaming and videos on my channel. And then I'm going to continue with the Saturday Spirit Science takedown, which has been kind of crazy, but people are enjoying it, so I'm going to keep going. And then Tuesday, I'm actually thinking about doing my 5,000 subscriber / slightly belated birthday stream on Tuesday instead of just doing the regularly scheduled Kenneth Bent.
Awesome. Awesome. So yeah, lots of good stuff over on your channel coming up. That'll be great. Cool. So for me, I am going to have another video 2 of my Weather 101 series goes up tomorrow. Those should be coming out Sundays and Thursdays because they're short, so I can do 2 a week. And yeah, okay. I'm going to let you guys go. Thank you so much for hanging out, and I will see you probably in 2 weeks. Bye, team.
Bye.